In this modulus of the MOOC, we will try to develop and to apply to a specific case study principles of durability assessment-based design according to the vision of the Horizon 2020 project ReSHEAlience. I am Liberato Ferrara, I am the coordinator of the project, and I am Professor of Structural Analysis and Design at the Department of Civil and Environmental Engineering in Politecnico di Milano. All the current, most modern structural design codes have durability as a fundamental requirement. I have put here some pictures, some examples of the covers of, for example, the FIB Model Code 2010, the Euro Code, and the structural design codes and documents of American Concrete Institute. And all these codes, all the modern structural design codes, they are based on performance-based design. So we have first of all to understand, in order to proceed further, we have to understand is the performance of a structure. The performance of a structure is defined as its behavior as a consequence of the actions to which the structure is subjected, or which it generates as a function and as a consequence of its interaction with the environment. In a performance-based design, it is prescribed that structures and structural members shall be designed, constructed, and maintained in such a way that they perform adequately and in an economically reasonable way during the construction, during the service life, and during their dismantlement in a circular economy concept. In this framework, we have to address, as structural designers, three categories of performance. The serviceability, which means that the structure must be fit for its use and has to be such, has to perform adequately under service, considering the combination of actions expected during its service life for its normal use. Then to consider the structural safety. Structural safety means the ability of a structure, of a structural element, of a structural member, to guarantee adequate stability, adequate deformability, adequate ultimate load-bearing resistance, corresponding to the actions which are assumed in the design, both under persistent combination, under accidental or exceptional situations. And these performances have to be guaranteed with an appropriate level of reliability, once again for a specified reference period, and for all possible damage states and exposure events. And finally, we have to consider that since a structure is fulfilling a societal need, this capacity of fulfilling the needs of the society, of the humankind, also with respect to nature and humans, must be guaranteed nowadays, but must also be done in such a way that the future generations will have the same possibility to fulfill their needs in the same manner. Actually, in the three performance categories that I have listed and explained so far, durability is not explicitly listed. And I purposely put here an image of the Pantheon, which nowadays is the longest still standing concrete structure in the world. Because when we speak of durability of concrete structures, we have to understand, first of all, whether durability is a material or a structural problem. And in order to do this, we have to go deeper into what the codes tell us about durability. Well, first of all, it is explicitly stated that durability is an inherent aspect of both serviceability and structural safety. The performance verification must be conducted considering in an appropriate way the evolution of the performance over time. This is the concept that we have to have in mind when we speak about durability. So according to this, we have to say that durability criteria are somewhat implicitly involved in the serviceability and safety design prescriptions and design algorithms. And that the performance verification that we make, once it is satisfied, is also meant to guarantee that performance over a specified service life, which must be assumed in advance, considering the requirements that are posed by the stakeholders. And the stakeholders are a variety of subjects: founders, owners, residents, users, neighbors, the contractor, design and construction team, tenancy management, maintenance team, the government, and the society up to the highest level, which may require some levels of performance over a certain service life as a common interest that the society has agreed upon. So what does the code, I put a reference here to Eurocode 0, so-called EN 1990. What does the code tells us that we have to consider when we design for durability? Which is the use of the structure, which are the design criteria, which are the environmental conditions, the composition, the properties and the performance of the materials and the products, the properties of the soil, because any structure will interact with the soil, but for being founded on it, the structural system that we have chosen, the shape of the structural members, the structural details. How do we build the structure? So which is the quality of the workmanship? Which is the level of the control that we have adopted in construction? Whether we are going to adopt or not some protective measures during the use, and which measures? And which is the maintenance that we have planned during the design service life? As a matter of fact, if you look, and I have highlighted with some colors in this slide, durability is considered as both a material and a structural issue, and it encompasses performance of the material and performances of the structure. So let's now try, since we are going to focus on concrete and advanced concrete and cement-based materials, let's try to be a little bit more precise in the context of concrete structure. What I have exposed in the previous slide was a common durability design framework referred to all the structures because it's contained in Eurocode 0, which is the global framework for all structural Eurocodes. But now let's try to focus on what Eurocode 2, EN 1992, states for concrete structures. And as a matter of fact, it makes reference to EN 206, which is the standard which gives common prescriptions, also superseding all the standards related to the constituents of concrete, but also to the testing of concrete performance for construction. As a matter of fact, EN 206 distinguishes, first of all, different exposure conditions. Very specifically, because some of the classes, the exposure classes, are further distinguished into subclasses with very specific requirements and very specific examples. And for example, we go from class X0, no risk of corrosion, no risk of attack, whether it be freeze and tow, abrasion, chemical, and so on, to class XC, corrosion induced by carbonation, further distinguishing 4 subclasses dealing with the humidity of the environment, which can be dry or permanently wet, oppositely wet, rarely dry, or moderate humidity or cyclic wet and dry exposure. These are the 4 subclasses from XC1 to XC4. Then we go to corrosion induced by chlorides, which are not from seawater, classified into 3 subclasses, XD1, XD2, XD3, once again based on the humidity, which can be moderate, wet, rarely dry, or cyclic wet and dry. Class XS, corrosion induced by chlorides from seawater, can be airborne salts, not in direct contact with seawater, class X1, class XS2, permanently submerged structures, or class XS3, tidal splash and spray zones. Then we have attack due to freeze and thaw cycles, with or without de-icing agents, differentiated, as you can see, into 4 subclasses dealing with the water saturation of the concrete and the presence or not of de-icing agents. So you go from moderate water saturation without or with de-icing agents, class XF1 and XF2, to high water saturation without and with de-icing agents, class XF3 and XF4. And finally, we have the chemical attack class, distinguished into 3 subclasses, XA, 1, 2, and 3, generally related as slightly aggressive, moderately aggressive, and highly aggressive. And we find in the same EN 6 standards some specific definitions related to the type of aggressive agents, sulfates, carbon dioxide, nitrates, magnesium, and also related to the content of this aggressive into the water, into the soil, even the pH of the water, which may discriminate about the level of acid attack for the environment the structure is exposed to. Depending on the class which is chosen for your structure, first of all, we find in the codes requirements related to the material. We have prescriptions related to their composition, maximum water cement ratio, minimum cement content, minimum air content, type of cement, and to their performance intended as a minimum strength class that we have to guarantee according to the different exposure classes. This is a table taken from Eurocode 2 according to the exposure classes dealt with in EN 206. So these are material performance requirements. Then we also are addressed to go for structural performance requirements. So first of all, to think of a structural class. Generally, our structures are designed for a service life of 50 years. So it could be a structural class number 4 according to the table in the top left of this slide. And then you can see that not only depending on the stress class, but also depending on the service life that you want to assume, depending on the quality control measures that you put into practice in the construction, depending on the structural geometry, you may play with the classes going for more strict or more relaxed requirements. In terms of what? Well, actually in terms, for example, of minimum cover prescriptions for ordinary reinforcement, as you can see here, going from class 1 to 6, we have class S4 as a reference, but going up and down, depending on what we have seen in the previous slide, you can see that if we go for a higher class from S4 to S5 or to S6, which means that we require, for example, a longer service life, we are recommended to adopt a higher cover. Whereas, if we can relax the structural service class requirements, we can go for lower cover requirements. This is a table that you find in Eurocode 2 once again for ordinary reinforcement cover, and a similar one, which is this one, for pre-stressing reinforcement. Obviously, in this case, since we know that pre-stressing reinforcement being stressed since the beginning is more sensitive to corrosion, we have a little bit more strict demands on the cover. And as a matter of fact, these are structural requirements. Like structural requirements are those which, for the different exposure classes, for the type of reinforcement, and for the combination of actions, we are given with reference to the opening of the crack that we have to calculate, or even to look for a decompression serviceability limit state under the frequent load combination, for example, in the case of a quite severe exposure conditions, like when we have high risk of corrosion from chlorides, whether they are not or from seawater, class XD and class XS. Actually, as I said, these are structural serviceability performance requirements. So in the codes, we have both material performance requirement and structural serviceability performance requirements. But there is a but. If we think a little bit in detail of what kind of approach is in the slides that we have reviewed before and which basically summarize what is in Eurocode 2, it seems to us that there are several prescriptions surely related to some performance, but we hardly have the feeling of really controlling a specific performance of the structure. As a matter of fact, in designing for durability, we have the possibility of framing our approach into 4 different levels. And if we review them from bottom to the top, they are the followings: avoidance-of-deterioration, deemed to satisfy approach, partial safety factor verification format, and probabilistic safety format. As a matter of fact, the current approaches which we find in the codes are based on avoidance-of-deterioration approach or deemed to satisfy approach. If we want to go for higher level approaches, we need to use, for example, deterioration model and to classify the environmental loads by means of parameters. And this is quite, there is quite an abundant literature on this for chloride. But when the codes were published, and actually the last one in order of time is the FIB Model Code 2010, such quantified parameters were not immediately and readily available in operational standards. So they should be found by measurements in the literature or case studies dealing with existing structures. But why we will need to scale up from the approach which we currently find in the code to a higher level? And I put here this explanatory graph. On the x-axis, on the abscissa, you have the time, the life of the structure. And on the y-axis, you have a performance. I put there a moment, a bending moment capacity. Well, from our structural analysis, we do have information, quantitative information, on which is, for example, the required load-bearing capacity in terms of bending. And when we design at time 0, we design so that we guarantee an MRD, a resistant value of the bending moment capacity, which is higher than the demand, the MED, the ones that we have obtained as effect of the action from structural analysis. We design with an initial safety margin. Obviously, in that initial safety margin, it's implicit, as we said, if we comply with the durability performance requirements, it's implicit the fact that this performance will decay over time, as the gray curve in this slide indicates, up to a certain point when it will reach a level which the stakeholders do not consider any longer acceptable, and this is the limit that we identify at the service life of the structure. Obviously, this is not exactly the failure, because the performance before reaching the failure still have some margin to go farther down and to become exactly equal to the action. Well, actually, in this approach, deemed to satisfy approach, we do not have any quantitative information about the service life. So we may need a higher level approach if we need to have a quantitative decision-making tool to plan the maintenance, to plan the end of life. When shall we start thinking of a major maintenance operation? When it will be more convenient to demolish and rebuild in case recycling instead of maintaining. The other thing is that these approaches are based on conventional concrete. And they are hardly adaptable as such to high performance material, which are nowadays becoming more and more common. I put on the left top part a guideline from ACI Committee 239 about ultra high performance concrete. And we do have other standards. So in order to coherently design with these materials, as far as durability is concerned, we need a higher level approach. And as far as the ultra high performance material, I have listed here a number of standards from America, from France, from Switzerland, from China, from Canada. Actually, in all of this, it's stated that the durability of ultra high performance concrete is superior to that of conventional concrete due to dense matrix and discontinuous microstructure. This is durability in the uncracked state. But also it's stated that the durability is superior thanks to well-dispersed micro-cracking of the material. And this is durability in the cracked state. So we have to distinguish this. Because these materials are surely intrinsically more durable in the uncracked state, but their way of working in the structure, thanks to a well-dispersed micro-cracking, will make them durable also in the cracked state, more durable also in the cracked state. So we need to adapt the design methodologies or to conceive the design methodologies, especially for these materials. And there is a scheme which I took from work by Mechterin and Altman, adapted, in which the design strategy is highlighted. We have on the left avoidance and limit to satisfy approaches, and on the right the higher level approach, in which, as you can see there in the green box, we have to understand, first of all, which are the durability indicators. Well, as a matter of fact, since we know that durability is superior to conventional concrete for ultra-high performance material due to dense matrix, discontinuous microstructure, let's try to focus on this now. We have first of all to consider durability indicators related to this state and related to the fact that all the process of interaction of concrete with the environment occurs in the presence of moisture, which may contain and veiculate aggressives. So, as a matter of fact, in a first instance, we have to look into transport properties. So, indirect indicators, as listed there, can inform on the potential durability of a specific type of concrete as related to its resistance to transport, and they are accessible porosity, permeability to gas or liquid, and capillary suction. Then we find in standards in the literature, actually in the project ReSHEAlience, we have reviewed the literature, and we have tried, for example, based on the information you can find on a public document, deliverable 3.2 on the website of the project, we have tried to categorize the level of durability from very low to very high based on the levels of water accessible porosity, gas permeability, intrinsic liquid water permeability, and so on. Then we have to go to consider also not only general interaction of the concrete with the environment, but also specific degradation processes, which can be, as they are listed in the table in the right part of the slide, the degradation of the matrix or of the fiber matrix interface or of the reinforcement matrix interface due to physical and chemical attacks, the corrosion of the reinforcement of fibers. And this can be due to chloride-induced corrosion, carbonation-induced corrosion, freeze and thaw attacks, alkali-silica reaction, acid and sulfate attack, delayed ettringite formation. These degradation mechanisms are the ones that are currently listed in FIB Model Code 2010. And I purposely put two of them in color because are the ones that we will focus on. Chloride-induced corrosion in green, because the code says there are models with a relatively broad international acceptance, so we can refer to them for our design. Or there are models which are still under discussion, like for acid sulfate attack. So we need to further do research and also validation with reference to real cases. For example, for corrosion, we know that the diffusion of the chlorides into the concrete is governed by the second Fick law of diffusion, which relates the derivative over time of a concentration of chlorides at a certain depth and a certain time to the second derivative with reference to a space dimension. This is for a unidimensional mechanism, and to an apparent diffusion coefficient. I reported the solution in terms of concentration, but also the solution in terms of the critical depth. The critical depth is the depth which, depending on the apparent diffusion coefficient, but also on the concentration of the chlorides at the surface and at the initial time inside the concrete, when this concentration reaches a value which we consider as critical, for example, for the initiation of the corrosion of the reinforcement. There are a lot of parameters that need to be calibrated. For example, the initial chloride content. And in EN206, we find, depending on the structural type we are considering, not reinforced, still reinforced, pre-stressed, the maximum chloride content by mass of cement which we can allow. So once again, this is a requirement on the material side related to the cement. Also, we have to consider which is the concentration of the chlorides at the surface of the structure, depending on to what kind of environment is it exposed. And you can see listed in the table the level of chlorides in grams per liter of different seas and lakes. And you can see that we go from almost fresh water in the Baltic Sea to average contents of around 30-35 grams per liter in Atlantic Oceans, in Pacific Ocean, in Mediterranean Sea, a little bit higher because it's a closed sea, to very high levels in Caspian Sea or in the Dead Sea. And obviously, this affects our serviceability of the structure over time, because we will have a condition at the surface which is different. Also, which is the critical content of chlorides that we can accept. A review made by Alonso et al. In 2009 categorized this in a frequency distribution plot, and you can see that there is an extremely large variability depending on the studies, because actually the mechanism is quite complicated. At the interface between steel and reinforcement, there are several processes occurring, as you have seen in a previous lecture of this MOOC. And also we have to consider that, well, we may have differences whether this critical value of the chlorides has been calibrated with reference to lab or field conditions. Also depend on the apparent diffusion coefficient of the concrete. Well, in the literature, there is a relatively broad agreement about the fact that values higher than 10 to minus 11 are related to ordinary concrete, 10 to minus 12, 10 to minus 13 are for high performance concrete. If we go for ultra high fiber reinforced, we go to 10 to minus 13. And also we have to consider that this may depend on the crack width. You can see a study made by Gerby et al. In 2008, how the value of the apparent diffusion coefficient can depend on the crack width, increasing with it obviously, but after that finding a sort of plateau as far as the crack width goes beyond some certain threshold values. Or we can consider also, this is a study by Cuenca et al. Published in 2018, that, for example, the self-filling may delay the penetration of the chlorides, so may also affect the value of the apparent diffusion coefficient that we may calibrate based, for example, on chloride titration test results. Some examples are given here. You can see that we go from a non-pre-cracked value, which is about 10 to minus 11. Well, if we have cracked without any self-filling, we go to values in the range of 10 to minus 9, 10 to minus 10, but the self-healing in the right column of the table, with self-healing and mixtures, we can go to values which are in the range of 10 to minus 10 and progressively decrease as long as the healing proceeds. Mechanism which goes with time, with the square root of the time, through a factor A, a proportionality factor A. So with time, you have a layer which progressively goes inside, a layer which leaches. So you can consider it as no more efficient to guarantee the structural resistance and the stiffness and the other performance. You have also this situation, you have to consider that it depends on several factors, like the ratio of soluble matter, which is the calcium ions, and the concentration of that in the face of the concrete or in the solution the structure is affected with. If you also have erosion because the water moves or you have solid particles moving, well, actually you have a linear term. So in this case, the degradation, in this case, you really corrode the concrete, you remove it, the degradation goes much faster. And we have, for example, equivalent calcium leaching coefficient, which have been calculated in a study by Alonso, where you can see how they go from values in the 10 to minus 10 range to lower and lower to values in the 10 to minus 11 range. And the quantification of the A coefficient in the case of leaching mechanism, where it depends on the square root of, or a quantification of the proportionality coefficient in the case of leaching and erosion. Do not focus on the exact numbers, focus rather on the order of magnitude, because actually, as we said, these are data which come from the literature and still need to be agreed upon. Well, this is the framework in which we move, and you can see, depending on the variability of these parameters, for example, as for leaching, you have the blue shadowed part of data dealing with ordinary concrete. The orange one is for high performance concrete, the gray one is for ultra high performance concrete. There is a significant difference. In the case of erosion, there is much larger uncertainty, and so the ranges in some cases overlap. But still, you can see that in some cases you lose a few centimeters in the very immediate years after the initiation of the service life. As I was saying, this is the framework, the theoretical framework in which we move, and we have tried to apply this concept into a durability design framework to a case study, which is one of the pilots of the project, ReSHEAlience. We will have a dedicated MOOC lecture on this later. It's a basin for water containment. It's geothermal water. It comes from geothermal drilling, so the water contains both chlorides and sulfates. And we made the pilot, you can see a picture there, the pilot into three different parts. You can see on the right a scheme. The red part is ordinary concrete. The blue part is ultra high performance concrete. And the green one, as you can see there, is a specific ultra high performance concrete solution in which we designed slabs and buttresses in order to have very, very, very thin elements. Well, matter of fact, let's try to simply understand how this structure works. The walls work as a cantilever, and the walls are 1.5 meter high, and the water level is given as 1.3 meters under service. So we calculated the action in terms of bending moment. And if we have to go for ultimate limit state combination or serviceability limit state combination, we have this gamma G factor, service permanent load condition. What does it mean? Well, if we are under serviceability limit state, it's 1, but under ultimate limit state, it's 1.35. What does it mean? Really, that the self-weight of water goes from 1,000 kilos per cubic meter to 1,350. Water is water, so its self-weight does not change. So we can interpret it as a wave surcharge effect. So actually, It means that, for example, if we go from 1 to 1.35, we guarantee that our structure, our cantilever wall, will not only work for water up to 1.3 meter level, but will be able to guarantee that level of performance up to about 1.45. So more or less completely full with no overflow. This is the meaning. We have calculated, so MED, if we refer to the specific Eurocode notation. How do we evaluate MRD, the resistance? So start, first of all, to understand which is the aggressive condition. These are some data from the waters from different geothermal power plants, and you can see that they can contain a lot of sulfates and a lot of chlorides as well. For ordinary concrete, it's quite easy. We know how to do that. Well, in the pilot, contrary to what normally happens, we have designed a 100 millimeter thick slab with feet 10 every 20 centimeter reinforcement and also some minimum horizontal reinforcement. The cover depth is 30 millimeters, so we can calculate the effective depth. And also, assuming a concrete C2530, we calculate the tensile strength, the flexural tensile strength, so we can calculate the cracking moment, average, and characteristic. This represents the onset of cracking at the serviceability limit state. Then we have to calculate the ultimate limit state, and also in this case our classical formula. We go from the characteristic to the design compressive strength for concrete and for steel, and we assume a very simple model, and we calculate the design bending moment, which actually turns out to be quite larger than also the design bending moment at the ultimate limit state. Now we want to embed into this algorithm the degradation model. So let's start first from chlorides. And let us use the solution of the equations that we have seen, solution of the problem, in terms of critical penetration depth, depending on the different values of the apparent chloride diffusion coefficient. We can say that up to the time where the critical penetration depth reaches the cover, 30 millimeter, there is no problem. If we have ordinary concrete cracked, as you can see from the graph in the left, the calculation, the solution, tells us that we need 18 years to arrive at a moment in which the chloride contents at the cover depth, 30 millimeters, reaches the critical level. If we consider healing, we will need 80 years, according to the values of the parameters that we have employed, which comes from specific experimental studies. Think that these are examples, are not of overall validity. Is how do we apply the algorithm, apply the methods with reference to parameters which we have found in specific internally recognized studies and investigation. Well, actually, if the concrete remains uncracked, you can see that the time is much longer. But can we really see that the concrete is uncracked? We have calculated that we are under service condition at the cracking limit state. So we may not be sure that the cracks will not form. First of all, because we are exactly at the limit. Secondly, because we may have cracks due to shrinkage, due to settlements, due to deformation, and so on. So anyway, before the chloride arrive at a critical content at the cover, nothing happens. When we arrive at this situation, the corrosion starts. So we need a model for the corrosion of the bar. And we have employed a very simple one, which you can find in the literature, where we decrease the diameter over time based on a parameter. We took a value from the literature and based on the average corrosion current density. So we estimated, just for an example, that every year, because of the corrosion, we lose 100 microns of layer around, of peripheral layer around the perimeter of the reinforcement. And so progressively, the area of the reinforcement is reduced. And you can see, applying this area reduction reinforcement, how fast is after that the degradation of the flexural performance up to the first time where the chlorides reach the critical limit at the cover, nothing happens. Then the moment capacity starts immediately decreasing. So depending whether we are considering a gamma G factor of 1.35 or 1, we have an expected service life around 47 to 57 years with these values of the parameters for ordinary concrete, in the range of a little bit more than 100 years if we consider healing, or much longer if we are with ordinary concrete but in uncracked situation. Once again, these are examples of how applying the degradation models, embedding them into structural design, and taking reference values of the parameters from the literature, we can estimate the degradation. Then we have to evaluate the serviceability. We know the equations, force and moment equilibrium equations. We calculate the stresses in the concrete and in the steel. For example, we can evaluate over time, look at the graphs on the right, how the neutral axis depth goes from the initial value, which is around 23 millimeters, rapidly decreases, or how the stress in the concrete, the gray and yellow curve, increases, and at the same time how the steel stress increases. Well, I have considered here a cracked situation, so we only have two curves, and look at the gray curve. The stress in steel after the corrosion starts rapidly increases and reaches, I put a 250 limit, which means that we are at around 1 per mil deformation level, and this corresponds to an acceptable level of crack opening. The time that it takes to reach this stress limit is lower than the one that we have calculated to reach the ultimate moment capacity due to the reduction of the steel area. So this means that the serviceability limit states, in this sense, are responsible for the design. They are more severe in terms of requirements. Well, a similar model application can be done for acid attack, but in this case, as you can see, the uncertainty of the parameters is much wider. So we have an estimate which spans over much larger time. Also in this case, if we have only leaching, we can say that nothing happens until the leached layer is the cover. But once we reach the corrosion starts, and so once again we have to consider this is the case of erosion. It's a very broad prediction. Once we lose the cover because of leaching or because erosion, the corrosion starts once again because the reinforcement is exposed to the aggressive water. And you have a very fast reduction. This is the prediction of the reduction in moment capacity due to leaching and corrosion. And in the next slide, you can find the prediction of the moment capacity reduction in the case of erosion and corrosion. You can see that the decay is really very fast. In the case of erosion, and in the case we have ordinary concrete of the worst quality, this means upper bound value of the erosion parameters, we have a service life of about 15 years. We can go a little bit higher if we consider a better quality ordinary concrete. It's written ordinary concrete lower bound, or if we use high performance concrete where the erosion parameters are still lower. Well, also in this case, we have then to evaluate the serviceability according to the same equations, force and moment, calculate neutral axis about stresses. And you can also see here, we have in light blue, orange, or dark blue, the curves showing how the neutral axis depth decreases. It's important, these parameters, because as you will see in the design, in the MOOC related to the design of this prototype, the depth of the compression zone is a design parameter, and you have to guarantee a certain compression depth because it's that guarantees water tightness. So if you go below a certain value, it's no longer acceptable. And as long as the depth decreases, the stresses in concrete and steel increase, and you see an analogous, very, very steep increase of the stresses in steel and in concrete, as long as you progressively lose part of the section due to leaching or due to erosion. In this case, is in some situations really very, very fast, and it may be in the range of few years or few 10 of years with this parameter according to this model prediction. Now we have to move to the ultra high performance concrete, ultra high durability concrete design. Ultra high performance concrete, ultra high durability concrete have a specific tensile behavior, which can be modeled as elastic perfectly plastic. You have seen in the dedicated MOOC lecture of this course. And similar one we can assume for compression. So in this case, the equations become very simple. Besides a compression stress block, which we are familiar with, we will have a tensile stress block as well. And we can also have a rigid plastic approximation in which we concentrate the compression force into a very thin layer up to a point, and all the cross-section is under the stress block of the tensile stresses, which are the design tensile strength of the material, provided that we can guarantee an ultimate deformation capacity that you can see there as epsilon TU, which complies with the deformation and ductility requirement of our structure. So remember, how do we calculate the resistant moment for the cross-section here? As a matter of fact, in the ultra-high performance concrete, ultra-high durability concrete solutions that we have designed for our water basin, we do not have any kind of reinforcement, only the fibers inside the concrete, which provide the reinforcement action and provide this ultimate tensile strength of 5.6 Newton per square millimeters, elastic plastic. So you can see once again here summarized the action and the resistance. We have twice as much reserve value. What does it mean in case we have an attack from chlorides? Well, it's quite difficult because there are not many data on that, but we can assume that as long as the chloride penetrates, the layer in which they reach the critical level, which contains steel fibers, it's not exactly this. We are assuming a very overcautious assumption, but we can assume that the few fibers in that surface layer are corroded and we lose them. So we make a very strict evaluation of the decay of the capacity. So as long as the aggression proceeds, we progressively lose some layers of our cross-section. And it's very easy. Simply you decrease the thickness and you evaluate accordingly the resistance. So you may have this decay level that you can see here in the blue, orange blue, or light blue curves, which are the values of the bending moment as they decrease along time, as long as the attack proceeds. And the gray, the yellow, and the green are the residual, the thickness of the critical layer. So you can see that, for example, if you use a value of the upper end diffusion coefficient, because this is the governing parameter, 10 to minus 11, well, we arrive at a certain point at a critical situation in which our design resistant bending moment is equal to the action, the value of the action at the ultimate limit state, 5, which means that we have a residual cross-section thickness of 42 millimeters, starting from an initial value of 60, because this is the value that we were able to guarantee in this case as a minimum to comply with the requirement. Or if we relax the ultimate limit state requirement, we go for 1, like an exceptional situation, well, we can go even later with degradation, and we can accept up to a residual cross-section thickness of 26 millimeters. Serviceability limit states, it's more difficult to evaluate them in this case because we will need a model for the calculation of crack openings and so on. I made a simple estimate here of the deflection, considering a cantilever beam under a water pressure level. So calculating the deflection and putting some limits. For example, when it's 1 over 200, the height of the wall, 1 over 100, or even some other limits. And you can see that once again, depending on the value of the apparent diffusion coefficient, 10 to minus 11, 10 to minus 12, 10 to minus 13, you may have different times in which you meet this threshold requirement. And once again, you see, for example, in the case you have 10 to minus 11 apparent diffusion coefficient, which means high performance concrete but not ultra high, you meet this serviceability limit state requirement, the first one, 1 over 200, the height of the wall, after 35 years, which is much earlier than when the ultimate limit state capacity is reached according to the previous slide. Obviously, you can reapply the same equations and the same procedure in the case of leaching or in the case of erosion. Simply, the thickness of the layer that you lose because of the degradation mechanism is related to the governing equation of the degradation process. So it could be A times the square root of time in the case of leaching, or could be a parameter key A times the time for the erosion mechanism. You make your estimate and you find your graphs. These are the estimates in the case of erosion. You can see that once again your critical thickness and your residual thickness is the same as we have estimated for the concrete mechanism, because the statics does not take that into account. In the case of erosion is much more severe, because you can arrive at losing the capacity at ultimate limit state in a range which may go from 35 to 55 years or from 45 to 65 years, depending on the upper or lower bound value of the erosion parameters that you assume for your concrete. Well, once again, if you use the dark blue curve, you can see that you have, if you have a very ultra high performance concrete with very, very low erosion parameters, lower bound written here, your degradation curve is much, much lower. So this highlights the benefits of using ultra high performance material. And once again, if you consider the serviceability limit state, once again in the case of deflection, you can see the orange, light blue and dark blue curves, how they represent the evolution of the deflection. Obviously, as long as you lose the thickness, your stiffness decreases and your deflection increases. And since the thickness goes with the cube of the thickness, as long as you lose the layer, the stiffness degrades faster and faster. And once again, you can see that you arrive, this is the case of leaching, this is the case of erosion, you arrive at a level where your performance is no longer guaranteed, deflection equal to 1 over 208 or 1 over 100, at a time which is much shorter than the one that we have calculated for the ultimate limit state. So once again, the serviceability limit states are design discriminant. Then we have designed a third structural solution, in which our walls are square plates which have been precast and then are installed vertically within some buttresses, some solid column-like supports. So in this case, in order to calculate the action, we need to go for a plate slab analysis. So I put the cover of the book by Timoshenko, Theory of Plates and Shell, at page 214 of this book. You can find the solution, which I have summarized here. You have the two-way bending moments with the maximum and minimum values that we have assumed for the design. Actually, what is critical, and you can see here from the values in the right, is the moment at the built edge. But you also have some maximum bending moment in the two ways at the mid span in both ways for the square slab. But let us assume the value which is highlighted there in red as a value which we assume for the design. Well, according to the same procedure that we have seen before, if we use 1.35, we have the moment degradation curves, which you can see here, once again in light blue, orange, and dark blue for the chloride degradation mechanism. And you can see that we arrive at maximum capacity for very long time, sometimes after 100 years or even more. Is this really representative of the behavior? So considering simply the maximum bending moment, or shall we make, for example, a yield line mechanism analysis, like in this case? Well, we did it. The slab thickness in this case is 30 millimeters, and we calculated when the maximum water height is equal to 1.5 meters, because it can be even higher, as you can see here. So in the graph here, you have the water surcharge over time. You can see that the capacity of this highly structural redundant structure will guarantee you a capacity of resist a wave up to 4 meters, which is inconsistent because the wall is just 1.5 meters. But as long as you proceed over time, you will arrive when the A becomes equal to 1.5 meters. You have very high times for this case, because in this case, the material is very, very durable and insensitive to chloride attack. For the serviceability limit state, we calculate also once again in terms of maximum deflection, once again from the tables, and in the right graph you have how the deflection evolves over time as long as the cross-section decreases. We also tried to make a 20 millimeter thickness of our wall, just as an example. And you can see here that in this case, you are really a very, very strict design, because if you have a high apparent chloride diffusion coefficient 10 to minus 11, which is typical of high performance but not ultra high performance concrete, in 2 years, you lose your load bearing capacity. You need to go for very, very low values of the parameter to have a service life, an expected service life, longer and longer as long as the parameter decreases. And the surcharge 8 in this case tells us that if we consider not a cantilever beam-like behavior but a plate-like slab-like behavior, so we work with yield line mechanism, water surcharge, and so on, we will have an expected service life of 100 years or more. Obviously, this relies upon the redistribution capacity of the structure, which is very important to be taken into account if we want to have a more realistic prediction. Obviously, we repeated also the calculation of the serviceability limit states, and you have the related results in the right-hand graph of this. Similarly, we proceeded for acid attack. In the case of a 30 millimeter thick slab, you have once again the moment reduction capacity curves in blue, light and dark, and in orange, or the critical front penetration curves. Or you have the erosion attack. In this case is much more severe, because as you can see, we arrive at losing the moment capacity in 15-20 years if we have a simply high performance concrete, or in 20-30 if we have a ultra high performance but we lower bound values, lower qualities. So the value of the parameters of the degradation parameters are quite high. This means UHDC upper bound in the graph. Similarly, we made the prediction with yield line analysis. In this case was much better in the case of leaching and also in the case of erosion, because we go from 15-20 years, from 30 to 40, and even higher in the case of better quality concrete. Once again, relying upon the redistribution capacity of the structure. Similarly, we made the calculations for the serviceability limit state in the case of 30 millimeter thick slab for leaching or for erosion, or in the case of a 20 millimeter thick slab. We repeated our calculation for ultimate limit states, for leaching, for erosion, with yield line mechanism, or for yield line mechanism with erosion, highlighting the benefits of a redistribution capacity. and for serviceability. I will not go deeper into these slides because the content is, repetitive, but simply how to highlight you how changing the parameters, we have different levels of prediction. This is the serviceability in the case of acid attack leaching for a 20 millimeters slab. This is the serviceability prediction in the case of a 20 millimeter slab in the case of acid attack under erosion. So coming up to the conclusions, we have provided a framework to incorporate the degradation mechanisms into ultimate limit state and serviceability limit states design algorithm, which allow us to trace the evolution of the structural performance over time and take into account at the same time the specificity of advanced cement-based materials. Going for specific structural geometries like the slab, we have highlighted also that we need algorithms which take into account the specific structural behavior, so a slab is not a beam, and that highly redundant structures are structures which exploit at their best the superior mechanical performance of materials like UH, the specific structural behavior, so a slab is not a beam, and that highly redundant structures are structures which exploit at their best the superior mechanical performance of materials like UHPC, like UHDC. Obviously, in order to do that, we need to calibrate durability indicators in the lab and validate them through full-scale experiments and reliable modeling algorithms. As far as the serviceability limit states, we have, validated algorithms for ordinary concrete, but for ultra-high performance concrete, which work into multiple cracking strain hardening regime, we need a methodology for crack width calculation and the correlation of the crack width with the values of the durability indicators. And most of all, we have just slightly addressed the benefits of the self-healing with reference to ordinary concrete, but we need a metadata analysis to quantify a healable crack width and correlate the recovery of durability parameters with the crack sealing levels that we have detected in our study. I thank you for your attention and recommend you to subscribe to the newsletter of our project for further updates. Thanks a lot.